Good morning, ladies and gentlemen. Today we're going to look at linear growth and decay and how we can use recursion relations to model linear growth and decay. Now, we use recursion to model simple interest equations or where an asset depreciates using the straight line method, meaning it depreciates by the same amount each period. And the two broad models we use are for linear growth, we get from one term to the next by adding a common difference. Linear decay, we get from one term to the next by taking a common difference. If we want to think about this graphically, well, we could consider the series on the left. The series on the left can be described as t0 equals 20. To get to the next one, we do the previous one and we take 3. So it's linear decay, and on the graph, we can see that at n equals 0, so n equals 0 here, we might be 20 high. When n equals 1, we're 17. When n equals 2, we're 14. When n equals 3, we're 11, etc., etc. Now, I haven't done that on a scale, but the important thing is this jumps by the same amount each time and therefore produces a straight line. Right. Now, before we apply this to simple interest, I feel like you should have a banking 101 lesson, because you've all seen banks, most of you have bank accounts, and most people have a terrible idea of how banks fundamentally make money. So let's go through this very quickly. Most people, when they ask how do banks make money, they will say they make it through fees and charges. They do a little, but that isn't the bank's core business. Their core business is not fees and charges. Their core business is what's called the interest rate gap. And let me explain. So some of you will be lucky enough to have a deposit. And let's say each of you has $100. What you do is you put that $100 in the bank. Now, if you think about it, what the bank does is the bank keeps your $100 safe, allows you to access it any time you want. And what do they charge for this service of allowing you to access the money whenever you want and keeping it safe for you? Well, the amazing thing is they don't charge you, they pay you to keep your own money safe. How crazy is that? What these people do is they put 100 each into the bank. And the bank, currently interest rates are quite low, will pay them a certain percentage of what's called interest. If you deposit money into the bank, the cool thing is you get an interest charge back. So let's say you leave $100 in the bank for a year, you might get $2 back. And all of these people have $2 back. Now, so far, this seems like a terrible, terrible deal for the bank. They are having to put money and infrastructure into security to keep the money safe. They have to fund ATMs all around the place to make sure people can access the cash whenever they want. And to boot, they're paying people to put the money in. However, people also borrow from banks. So our miniature family over here needs to borrow to buy a house. Let's say they borrow $400. And this $400 doesn't just magically appear. The $400 comes from the deposits of these people. So banks can't just magic up money, it comes from the deposits. Now I'm oversimplifying it here, and clearly you can tell that with the numbers, but there's the point to get across the interest rate gap. There's a money multiplier in there as well. But if $400 goes to the people, at the end of each year, or realistically each month, the bank will ask for an interest charge. And the bank might charge 4% interest, which means 4% interest on $400 is $16. So the bank has money coming in from depositors, going out to families borrowing houses or cars, etc. And this gap that appears is called the interest rate gap, and that's what gives them money. The bank has lost $8 but gained 16. So overall, the bank is up 8. So when we talk about depositing money in or withdrawing it out, you've got to remember which way the interest is going to flow. If money has been deposited, interest will flow back to the person depositing. If money has been borrowed, interest will have to flow back to the bank. Interest is effectively the charge of borrowing the money. Alright. Now, recurrence model for simple interest. And if I were you, we're going to do simple interest and then some depreciations. After we do each of them, can you just leave a gap underneath? In a later video, we'll come back and add into that gap. Alright, so the question here is, what is the value of a simple interest loan? Oh goodness. For the first 4 years, if $1,500 is deposited at 3% interest. So, using recursion to do this, we can use this guideline here. The initial value is the principal. Principal meaning the amount we put in the bank in the first place. So here, our initial value is $1,500. That's the amount that's been borrowed. Then, the value of the loan, or the amount owed, can be gained by, or be modelled with this part of the recurrence relation, where Vn plus 1, so how we get to the next year in our time series, is equal to Vn plus D. Now D is the common difference, and in our case, D is equal to R on 100 times VO. What D is the percentage increase or decrease each year. So it's 3 on 100 times 1,500. Which comes to $45. Alright. So the recurrence relation is Vn plus 45. Now what that means is that each year $45 interest is charged onto the simple interest loan. So to model this using recursion, we would say, well, if VO is equal to 1,500, V1 is equal to 1,500 plus 45, 1,500 and 45. V2 is equal to 1,500 and 45 plus another 45, etc. Now what this number is representing is the amount of money that's owed at the end of 4 years. So we started at the start of the first year with 1,500 in the bank, or rather borrowed from the bank because it's a loan. Then at the end of the first year, the bank has charged us $45 interest. That's fine, we now owe that amount. At the end of the second year, another 45, third, and the fourth year here is how much we're going to have to repay at the end of the period. Alright, leave a gap in your books there, and we're going to go on to depreciation. And I'll do this quickly. So, depreciation is when an asset loses value over time. There are several ways to model depreciation. There are two using linear recurrence. One of them is flat rate depreciation, the other is using unit cost depreciation. So, flat rate depreciation is where something loses a certain percentage of its initial value every year. Note that flat rate means the percentage is always of the initial value, it's not of anything else. So here, it's not of the value of the year before. So here, a $7,000 TV loses 20% of its value per year at a flat rate using recurrence. So VO here is 7,000, that's the initial amount, and then the recurrence relation is given above there, where D, once again, is this percentage of the original. Now 20% of the original is 1,400, so Vn plus 1, we get to the next year's value by taking the previous year's and subtracting 1,400. So how much would be worth after 3 years? VO is 7,000. At the end of the first year, it would be 7,000 take 1,400, so 5,600. V2, we take another 1,400, 4,200. And the end of the third year, we take another 1,400, 2,800. So this television at the end of the third year will be worth $2,800. Alright, once again, leave a gap, then here. Assets depreciate based on usage. Basically, exactly the same thing, except here, the difference is the amount that it loses each time. Alright, and I'll leave you to do that one, because we're running out of time. Thank you very much.